are in your second slide.
Yes, good.
Okay, is it streaming? So welcome everyone to today's seminar. Today we have Facundo Gomez, who is an associate professor at the University of La Serena in Chile, and he's also the co-director of its PhD program in astronomy. He got his bachelor's degree from the Universidad Nacional de La Plata in Argentina, and then later on a PhD from the University of Groningen in the Netherlands. He held postdoc positions at Michigan State in the US and the Max Planck Institute for Astrophysics in Germany. His research focuses on the formation and evolution of galaxies, with particular emphasis on the dynamical processes, cosmological simulations, and the origin of morphological perturbations such as warps and lopsidedness. He's also an associate researcher at the CATA and actively contributes to the training of graduate students and the development of international collaborations. Thank you so much, Facundo, for accepting our invitation. You may start when you're ready.
Thank you very much for the introduction, and hi everyone. So I'm very happy to be here today through Zoom, sharing a little bit of the work that I have been doing here with a member of my group at La Serena, as Anna mentioned. In particular, today I'm going to mention a bit of the work from a postdoc, Ariel Adolfi, and a previous PhD student, now a postdoc in Franklin Atlas. And the idea is to see what we can learn about the formation and evolution of galaxies through morphological perturbations and ongoing activity. So I like to start this particular talk with this very nice picture that I took last year here in Chile, in the area of Puerto Varas, which is the Saltos del Petrohue. This is a very old structure, basically dates from approximately 50,000 years ago. And what you can see in the picture is the volcano Osorno, in addition to this very nice structure that is composed of basaltic rocks. The origin of this is most likely associated with an eruption of this volcano, which injected a lot of basaltic material, solidifies, and then through the course of time, due to the rivers and the streams of water that you can see in the picture, all these structures start to take a different shape and started to evolve. So by looking at this very beautiful structure that has been created by nature, we can learn a lot about the evolutionary history of this region, this particular region of the Patagonia in Chile. So the same idea can actually be applied to galaxies, right? When we see a galaxy, we see a very nice structure, we see disks, or we can see elliptical galaxies, but all these galaxies, they have perturbations to their sort of otherwise smooth morphology. For example, we can see galactic disks that they have the very well-known spiral arms with different pitch angles and different structure. We see bars, but when we look to the outer structures, we see also, for example, in the stellar halo, we can see stellar streams, like here, for example, from the Sagittarius dwarf galaxy, material that is being released by tidal interactions. And we can also see perturbations to the global morphology, such as in the disk, for example, again, lopsidedness in this case, and warps. So all these perturbations can be dated back to previous probable interactions or eruption, star formation bursts, or different processes that are shaping the structure of the galaxies that was at the present day. So they have clues about the evolutionary history. So today in this talk, I'm going to, I have been working with all these sort of different perturbations, but I'm going to focus on lopsidedness in the first part of the talk. And so what you see here is a picture of this M101 galaxy, which is a classical prototypical type of lopsided galaxies. When we see a lopsided galaxy, what we are talking about is this kind of structure that you see that is stretched along one direction, in particular in the light and also the density distribution of the galaxy, and is compressed in the opposite direction. So when you see this kind of structure, this is what we typically call a lopsided galaxy. So we more or less know what we are talking about. They are typically characterized by an m=1 mode when we do a Fourier decomposition. So why lopsided galaxies are important? Well, when you observe galaxies in the nearby universe, you see that it's a fairly common perturbations in the disk. Up to 30% of later galaxies show significant lopsidedness. They used to be, or the people tend to claim that they are more common in these environments, although this is something that we wanted to study. It is the mode in terms of Fourier amplitude is stronger typically than the m=2 mode, so it could have very important implications in the dynamic of galaxies. And because it's an m=1 perturbation, it can be seen as a shift of the disk center of mass with respect to the center of density. So what happens is that you have the center of density, or wherever you want to put your reference frame, or your center of mass, moving around the other points, and that will induce torques throughout the disk that can have an impact, as I say, in the dynamics of the stars in the disk, in the star formation activity of the disk, because the gas is going to be torqued, it will lose angular momentum, and it will be drifted to the inner parts. And as a result, it could even enhance the growth of the central black holes, supermassive black holes. The origin for this perturbation is rather varied. I mean, and this the proposed different origin can be due to, for example, asymmetric gas accretion from the environment. It could be due to recent tidal interaction with satellite galaxies or flight bypasses, and it has been even discussed the possibility that perturbations on the density of the underlying dark matter halo could induce torques in the disk that could also end up resulting in a lopsided perturbations. So what was the goal of these projects? Well, the idea, how do we measure lopsided before I go to that? In observation, the typical way to analyze whether a galaxy is lopsided or not is to go to the near infrared, because there we have negligible dust extinction, and therefore we are sort of sampling the oldest stellar population of the galaxies, and as such, the light distribution can give us an idea of the density distribution. When we have this distribution, you can get the Fourier transform of the light mass distribution. And what you typically see, for example, in this example of NGC 1325, is a profile of a radial profile of A1 that as we go farther out, so initially it's very small power in the A1, but it starts to get higher as we get closer to the optical radius of the disk. So basically the inner parts do not show this internal lopsidedness, but the other part is where we see all this deformation in the morphology. Something that characterizes lopsidedness is the phase angle of this perturbation that is typically constant across this range, right? So this is the signature that we observe when we see lopsidedness in the nearby galaxies. So yes, now going back to the goals, I mean, the idea was try to see whether we can study the origins and the evolution of lopsided galaxies by looking at fully cosmological numerical simulation of the formation, in this case, of late-type galaxies, right? So for this first project, we started looking at the illustrated TNG50 simulations. These are a well-known suite of simulations. In particular, TNG50 has the advantage that it has the highest resolution among the suite. What we did is to look for Milky Way-like central subhalos, so halos that are in the mass regime of between 10 to 11.5 and 10 to the 12.5 solar masses. So those were the halos that we were looking. And we selected galaxies that had a disk to total mass ratio larger than 0.5. This based on dynamical arguments, like we used to use polarity parameters. So we selected these like galaxies in this sample. Because of the resolution that we had in terms of stellar mass per particle, we made sure that all our disks have at least 10,000 stellar particles. And as a result, the disks are reasonably well resolved in terms of numerical resolution. And the sample in this first study was about 240 disk galaxies that we could study. So just to show you an example of a lopsided galaxies in the model, you can see here in this plot, you see a very beautiful disk galaxy with the spiral arms and this very clear signature of lopsidedness, where you see here less light or density than in this region at the same basically radius. And what I'm showing here are A1 profiles for different examples of lopsided galaxies in the simulations. You can see the same sort of feature, right? The inner parts are rather symmetrical, but when we get about half of the optical radius, or basically the half-life radius of the galaxy, we start to see an amplitude of the A=1 mode that start to grow, right? Becoming more and more stronger as we get to the outer parts. If we select non-lopsided galaxies, you see the opposite, right? You see an A1 profile that is close to zero across the whole this extension. So we selected the galaxies and we measure a number of parameters that are kind of characterized in a global way. Each of these galaxies, for example, half-life radius, central stellar density, quantified is like the stellar mass within R50, and computed the central stellar density within a region, and the stellar concentration, which is the R90 divided by the R50, right? So we had all these parameters, and the first thing before studying these lopsided galaxies in the full sample, we wanted to make sure that the amplitude of lopsidedness that we see in the models is sort of comparable with what you could see in the nearby universe. If we get the simulations and all our simulations are strongly lopsided, then it may not make a lot of sense to study this simulation. They are not reproducing what we observe. So the first thing is to see the distribution of A1. So what I'm showing here is basically the average lopsidedness measured approximately within half-life radius and the optical radius. So in the outer parts, we take an average A1, and we make a histogram for each galaxy of one average A1. So we have the histograms. This is taken from a Sloan Digital Sky Survey. This is a study that Richard did in 2008, where he had 25,000 galaxies, a lot of them. And this is the distribution of A1 for the full sample. So you see it has sort of this peak distribution around 0.1. And so what they decided to do is to say, okay, everything that has an amplitude of A1, average amplitude of A1, larger than 0.1 is considered as lopsided. And the things that with A1 smaller values are considered symmetric. So when we look at the distribution in the models, we see a similar distribution to what is obtained, so reasonably consistent with the observations. And the threshold that we took is also 0.1. What I'm showing here is the median. And so we see again that the peak is about 0.1. So we decided again to define as lopsided and symmetric based on this threshold. Something else that we did is because we wanted to find the largest difference between the two kind of galaxies. We selected samples which are the 25% most strong asymmetric galaxies and the 25% less asymmetric galaxies to see the largest difference between the two samples. So when we say a strong symmetric and a strong asymmetric, I'm talking about these two subsamples that we have selected. So general properties of this sample of galaxies. The first thing that we computed was these two total mass ratios to see whether there were significant differences, and this is what I'm showing here. The dashed lines are the strongly symmetric and asymmetric, and what we see is that the lopsided, basically asymmetric galaxies, tend to be more disdominated than the symmetric. So basically in the symmetric galaxies, the central, more spheroidal, if you want, bush-like components tend to be a little bit more prominent than in the lopsided cases. Remember, this is all for the simulated galaxy, right? If we look at the concentrations, we see that there are no important difference between the two samples. The stellar mass distribution for the two samples is sort of similar. Where we do find very important differences are in the extensions of the stellar disk. This is the distribution of R50. So you see that asymmetric galaxies tend to be more extended. And in the central stellar density, as I said, measured within R50, we see that lopsided are less dense in the lower central surface densities for the lopsided galaxies. So what this is pointing to? Well, before, here you have the gain from the Sloan data, the same sort of analysis done with observed galaxies, and you see again, for example, at a given concentration, for the observed galaxy, we see that we can find all kind of values of lopsidedness. All right, this color coding means the median A1 for each galaxy in these beams. So you see that for a given concentration, you can find a lot of different values of lopsidedness, so there is not a strong correlation with what we see in this panel as well. But we do find observationally a very strong correlation between mu star, which is the central stellar density, and lopsidedness, right? So it grows, A1, the color, it goes from red to blue, and we increase mu star. So what this is pointing? Well, this is pointing to this self-gravity. Another way to explore this central stellar density is by computing a proxy for the tidal force exerted by the central regions on the outskirts of the galaxies. What we did here is compute this M50 that now is not only stellar mass, but also includes the gas mass and the dark matter mass within R50. And we compute this parameter, which is M50 divided by the optical radius to the power of 3, which would be a proxy of the tidal force exerted on the external regions by this central region. And when we do that, we find, this is the parameter that I'm talking about, we see that asymmetric and symmetric galaxies are very well distinct populations exploring this parameter. What is this telling us? That basically lopsided galaxies are less dense. As a result, they are less self-gravitating. I mean, the cores are not so strong, so they are not so cohesive in terms of gravitation. And what happens is that with these galaxies that are loosely, not loosely bound, but more loosely bound than the symmetric, whatever happens to them may actually induce a lopsided perturbation. It could be a satellite. I'm going to explore this later. It could be a flyby. But because they are not strongly self-gravitating, the galaxy will start wobbling once it suffers perturbation from the environment. So why these galaxies are basically less cohesive, right? Why they have larger R50s and why they have lower central stellar density? Well, what I'm showing here is the average mu star for the lopsided galaxies and for the symmetric galaxies. You can see that as a function of time, for the lopsided galaxies, mu star is going down, whereas for symmetric galaxies, sort of remaining constant. If we see the mass within the R50, the mass is growing sort of at a similar rate for the two samples of galaxies, but the half-life radius is increasing much more rapidly for the lopsided galaxies than for the symmetric galaxies. We can see in this plot how they start diverging one from the other sample. Why is this? Well, when we were analyzing the first suite of simulation from the Auriga project with Robert Grant, what we explored is the relation between this size and the spin of the dark matter halo. We wanted to understand what makes these galaxies larger or smaller in this cosmological simulation. And what we found is that the most important factor that leads to compact disk, or the other way around to very extended galaxies, is the spin of the underlying dark matter halo. Galaxies that are growing within high spin halos, they tend to have larger disk as measured by this parameter RD, which would be the scale length of the disk. And galaxies that are living in, and the opposite happens as well. Galaxies, the small concentrated galaxies, they tend to live in small spin halos. What we try to do with Silvio then is explore whether there is a correlation between the spin of the dark matter halo and the amplitude of lopsidedness. And actually, we found this plot where you see here the lambda parameter, which is the spin of the halo, this tidal torque that I was taking, the proxy for the tidal torque from the inner regions on the outskirts, and the color coding means whether galaxies are lopsided or no. Red is strongly lopsided, blue is symmetric, and you see that all the red points tend to live in a region of high spin parameters, whereas the symmetric galaxies tend to live in regions of low spin parameters. So when we found this, I found it very interesting because that was one of something that we were actually looking for. I mean, like this halo connection, right? You could say that by looking at lopsided galaxies, you could actually be inferring something about the properties of the dark matter halo where this galaxy is living, right? Is being hosted. So, okay, this is with regards to the present-day galaxy. So the idea is to say, okay, we know some properties about the lopsided galaxies. What we want to know now is what induced the lopsidedness. What are the main mechanisms driving this parameter, this perturbation? So I show here a couple of examples of lopsided galaxies. What you can see in these galaxies again is that they are becoming more extended. These are R50 and R90 as a function of time. They are growing, as I just said before. And in these two cases, we see that the central stellar density is decreasing with time. In both cases, these are actually low values of mu star with respect to the rest of the sample. And we find an A1 parameter that is rather large at all times throughout the full evolution of this galaxy. Remember, this is the threshold that we define to say whether the galaxy is lopsided or not. And in these two galaxies, basically A1 is always above this threshold. So it has always been lopsided, at least within the last 6 gigayears. So we say, okay, is this due to satellite interactions? So what I'm showing here is again a proxy now for the tidal torque exerted by the satellites on the disk. So what we are measuring here is the mass of the disk, the satellite, sorry, divided by galactocentric distance where the satellite is located to the power of 3. What I'm showing here are the 5 most massive satellites at every single time, every snapshot in the simulation. When you see a value that is high, it means that there is a strong tidal torque exerted by the satellite on the disk. And the color coding indicates the infold mass of the satellite. So, for example, in this case, you see a very massive satellite of the order of 10 to the 11, 10 to the 10.5 total mass falling down, going through the inner part of the galaxy, and you see the A1 parameter reacting to this interaction, right? You see this peak in the A1 that after the satellite goes down, disappears, the amplitude starts to fall down again, but remains with a high amplitude. However, in this case, for example, we see this lopsided pattern, but non-important or significant interaction. So in this case, this satellite is interacting here is really low mass, it's 10 to the 8, so it cannot do anything global to the galaxy, but A1 still is very massive. So we have an example that we can explain through interaction, but an example of lopsided galaxies that no interaction can be measured for this galaxy. Now, let's look to the symmetric galaxies. In this case, you see they are not growing, as I mentioned before. They tend to have a size set at least 6 gigayears ago, not much. If you compare the central stellar density, you will see they have higher values at all times. And you see that the A1 is sort of always below, or sort of most of the time below the A1 threshold, right? They have very low value of A1. I compare again with the previous cases. So if we see the interaction, for example, in this case, you see that this galaxy has a very, like 2 gigayears ago, had an interaction of with a satellite of 10 to the 10.5 solar masses. Again, a very massive interaction, but A1 is not reacting at all. So we have this very strong pass, very close passage, very strong interaction, but not lopsided perturbation is arising. Why is this? It's because the disk is very strongly cohesive. Instead of being deformed, most likely what is happening is that it's shifting or rotating as it happens, like when some satellites can pass, it can turn the disk. If the satellite is strongly cohesive, what happens is that the disk tilts. If it's loosely bound, what happens is that warps. So the same happens with this kind of lopsided perturbation. So in this case, we cannot find really, if we see a lopsided galaxy, can we claim it's due to tidal interaction? No. Other mechanisms have to be involved. And I'm going to explore some of these mechanisms in what follows, right? I'm not saying that lopsided is not associated with tidal interactions. I'm just saying that it's not the only mechanism that is required to explain all these type of perturbations. So, okay, so far I've been looking at Milky Way-like galaxies. So with Ariana, what we wanted to do is to increase the sample. Let's consider still this galaxy, but now considering a more open mass range to analyze. So in this case, what we did in this second study is consider galaxies with the total stellar mass larger than 10 to the 9 solar masses. So we go from dwarf to very massive disk, whatever can be found in the simulations. Again, we selected this galaxy by imposing a threshold and the disk to total stellar mass ratio. And we also focus on the same sort of numerical resolution for the star particle, right? We also independently, we went down in mass, but we also only select galaxies that had at least 10,000 stellar particles so that we can resolve the structure of the disk. In this new sample, we had about 1,100 central disk galaxies, but we also obtained a sample of satellite galaxies that live in groups and in some cases clusters. You can see here the mass distribution of the dark matter halos where these galaxies are living. If they are central galaxies, it's their own dark matter halo. If they are satellite galaxies, what I'm showing here is the mass of the structure where they are living. And the two populations have in total, the galaxies, the central galaxies, they have very similar distribution of total stellar mass. There are no strong biases in terms of whether I'm looking at more massive or less massive galaxies for the symmetric and the lopsided. These are the medians, so you can see there are very, very similar medians. Again, the distribution of A1 is very similar to what we get in Sloan. So, okay, this is good news because it says that we can try to get some information from these models. And what this larger sample allowed us to do is to see whether there was any sort of statistical correlation between lopsidedness and environment. To do that, we focus on some classical, basically parameters that measure environment. For example, we compute number of neighbors that the galaxy have within R200. In this case, with total mass larger than 10 to the 9 or in 10 to the 10. And we see that there is no an increase of A1 as we increase the number of neighbors, right? Our models do not show a correlation between how many massive satellites are around and how large, on average, this A1 parameter is. We could also do this as a function of volume density, like choose the 5 most massive galaxies, in this case, again, 10 to the 9 or 10 to the 10. Select the volume that these galaxies are living and compute the volume density and see whether, I mean, if these 5 galaxies are very close by, you would expect a stronger maybe lopsidedness or a stronger perturbation. But again, there is no correlation between A1 and this measurement of environment. I mean, this way we are quantifying environment. So what this shows again, that more than environment, again, lopsided galaxies are pointing towards the internal properties of the galaxy. Environment is important if the conditions are given, right? If the galaxy had the properties that are required to develop this lopsided pattern. So with this in mind, with the master student, actually I forgot to mention at the beginning when I introduced the people that have been working on this, Valentina Fontiroy, what she did is to do, she had in mind, okay, it's only environment, it's not environment, it's internal parameters. So what if we develop a random forest classifier and see whether by feeding as features only internal parameters of the galaxies, where we can recover a population, the properly separated population between lopsided and symmetric galaxies, right? And that's what we did, basically. We trained a random forest classifier based on parameters that have mass, optical radius, half-life radius, concentration, this to total, all things that can be extracted from the inner properties of the galaxy and no at all information of the environment where the galaxies are living. And what I'm showing here is the confusion matrix that we obtained from this random forest classifier. So in general, we find 80% accuracy with this model in dividing samples of lopsided and symmetric galaxies, which we consider rather high, again, based on the fact that we are only using internal properties, right? I mean, that this is confirming our hypothesis that lopsidedness is mainly related to internal parameters. Something interesting that Valentina also did is try to retrain the random forest classifier only using observable quantities, right? Things that you get from photometry or from surveys like splash or shape paths. For example, star formation rate, this extension, and C/A. And only with these 5 parameters, for example, we got still the same accuracy that using all this huge number of the features that we fed, the same accuracy in our selection from the random forest. So that was interesting. So now let's look a little bit at the assembly history, the differences, or why, again, going back to the question, why this galaxy had these very different internal properties with respect to the symmetric ones. And the first thing that we try is to look at the star formation histories of the galaxy, right? So what I'm showing in this plot is the fraction of stellar mass as a function of time. How is it growing, the mass of the galaxies as the time goes by. And what you can see is that basically this is telling us that symmetric galaxies, they typically have a very strong star formation burst at early times, about 8 gigayears, where most of the mass is formed, and then the star formation rate decreases, falls with time, until the present day very steeply. Whereas what we found for lopsided galaxies is that we have a sort of a mild growth at early times, basically this is 10 gigayears ago, and then at some point they start to have a constant star formation rate and continue to form stars up to the present date with a similar value. Here I'm showing actually, for example, for this mass range, the star formation rate, and you see a burst at early times and then a very sudden drop. Whereas for lopsided galaxies, a milder star formation rate and then a constant star formation rate up to the present day. So for example, if we look at the cumulative mass fraction, we see that in this case, basically this could be the T50, right? When the time when these galaxies assemble 50% of the present day mass, and we see that in general, lopsided galaxies they tend to assemble that mass about 2 gigayears earlier than lopsided galaxies. They do it at later times. So they are assembling in different ways in a statistical sense. Now, if you divide the galaxies within inner and outer region, you see this trend more clearly. Inner, let's say, R50, and outer, everything outside R50. We see that for symmetric galaxies, this could be the inner region. There is a very strong burst, again, as I said before, and then it steeply decreases. When we go to the outer regions, we see also a milder burst, but the same falls with time. Now, for the lopsided galaxies, we see for the inner region, a burst in the inner node, much milder than for symmetric. The fall, the interesting thing is the outer region, right? That we see now is continually growing up to present day with a very high star formation rate. So this is where the difference lies. I mean, how these galaxies, and this also explains why the galaxies are becoming larger and larger, right? It's basically accretion of cold gas, probably with higher angular momentum, which is something that we're exploring at present day with these simulations. So with respect to lopsided, I mean, two additional things is like, as I said before, this is a 101. This is a prototypical example of lopsided galaxies, and it's also a prototypical example of a bulgeless galaxy. So as I said before, lopsided galaxies tend to have lower central stellar density, so one would expect that maybe they are closer to galaxies with less significant bulges. And what we show here is basically the bulge over total ratio for simulated galaxies. In this case, the B over T has been computed in a very similar way as done in observation photometrically. So we make the fits and we remove signatures of the bars and things like that. So we get the bulge to total light ratio. And we see that there is a trend that basically bulgeless galaxies tend to have A1. So in a way, lopsidedness could be also a good proxy for searching for bulgeless galaxies, right? Remember that this is a property that is very easy to see. Like you get a picture from a galaxy, just the software brightness from the galaxy, and you can extract maybe, this is what we want to test with observation, all this information about star formation rates, bulge properties, and even maybe spin of the Darmatragelo, just by looking at an image like this. So what are the next steps in terms of lopsidedness? Well, something that we are doing now with some collaborators also from Brazil, with Fernandez, Ferrari, Ariana Cortesi. We are looking at both shape paths and S+. Why? Well, first of all, because we have very nice images in the optical, so we can get basically the images and classify visually by shape between lopsided and symmetric galaxies. But also, all these surveys, they have these multiple photometric bands. And because they have so many bands and typically many narrow filters, you can have something that is like a EFU sort of photometric analysis and try to derive from this light proxy for the star formation histories. And with that, we could actually test all this story about whether they have the burst or non-burst and whether they have these different star formation rates at present day. And we can also measure properties like the size of the disk, central surface density, exactly. All this information can be obtained from this survey. So just to give you an idea, can we do this, for example, with the S+, like we should see here the star formation rates from these two. This is a very wide range of stellar masses, so that's why it's so noisy, but You see the average, the different I was mentioning, the birthday and then the fall of the star formation rate, and here the constant. If we would have only three estimate of star formation basically of star formation history, right? Taken from the observation, like for all population 4 to 10 gigayears, intermediate 0.5 to 4, and young the last 0.5 gigayears. This is what we would get from these samples of galaxies that are making this plot. So what we're trying to do with this survey is something of this style. I mean, trying to see we can find differences on this estimation of star formation rates and histories from the observed sample from these two surveys. One additional thing I wanted to mention is that in a recent article from a couple of people working with JWST, we're looking at morphology. Now there are all this huge number of articles looking at the properties of galaxy at very high redshift, and they start measuring also lopsidedness at redshift up to redshift 3. So you see here an example of 2.3. And what they did is to select 22 infrared selected star forming galaxies, and they measure a lot of things, including whether they were lopsided or not. And what they find is that 64% of the galaxies that of these 22, okay, the sample is not huge, but remember this is redshift between 2 and 3, so it's significant. 64% of the galaxies show a lopsided pattern at this high redshift. You can see some example, in particular this one, a very nice example of a lopsided galaxy. So they discussed the possibility that this could be due to a higher rate of asymmetrical gas accretion at those early times. Or, this is a period of more major measure, right? I mean, galaxies are interacting with more massive satellites at those times. And because of that, they could be in constant interaction, and lopsidedness could be a more common phenomena than what we see at present day. Remember that at present day it was up to 30%, and now we are finding 64% of population being lopsided. So we did a brief exploration in our simulation. We only reached to redshift 2 because of snapshot limitations. We find something interesting, like the fraction of lopsided galaxy you can see here in black. Actually, in the models also fall from about 60% to, in this case, 40%. So we see these trends where, as we get closer to redshift 0, the galaxies become more and more symmetric. They were more asymmetric at previous times. But independently of that, we see still this correlation between A1 and central stellar density, right? This is different lines are different redshift. So this is redshift 0. You see the A1 grows as we decrease the mu star. And the same happens at all redshifts, just the fact that there is a shift towards a higher amplitude of A1, but there is a correlation still with mu star. So based on the description that they were discussing in this paper from Level and from the JWT, say, okay, let's see whether we find a lot of interactions that can be driving this lopsidedness. What I'm showing here is basically as a function of redshift, the fraction of galaxies that have a strong interaction, basically a 1 to 10 companion within half the virial radius. We compare symmetric galaxies, this orange, with lopsided galaxies. And indeed, we see that lopsided galaxies that more commonly have a massive near neighbor than the symmetric galaxies. However, the number of star galaxies that are lopsided that have near neighbors, significant neighbors, is about 20% of the lopsided galaxies. Not all of them, they have a significant perturber close by. So, okay, we see interactions, but this is not enough to explain the large amount of lopsidedness that we observe. What we do see is the mean net accretion rate, which is basically the mass that I have a snapshot minus the gas mass that I had at the previous snapshot, plus the stellar mass that has been the gas mass that has been transformed into stars. So this tells me whether my total gas mass is growing or decreasing, and it's a way to measure whether I have significant accretion from cold gas. And this does show a very significant difference. I mean, lopsided galaxies tend to have always positive mean net accretion rate, so I'm always accreting more than what I'm star forming. it's always positive with asymmetric galaxies that tend to have negative net accretion rate. So are basically starting to get depleted as we get closer to redshift 0. So based on our result, we see that at high redshift, for sure, there is a very important role of asymmetric gas accretion driving lopsidedness. So we are still exploring this, but that would point towards more this mechanism than rather a lot of interactions. So to follow up this analysis, now we want to increase our numerical resolution in order to be able to see more details on how this lopsidedness evolve. For that, we are using a new suite of simulation. I don't know whether you have heard about the Auriga simulations in the past, but there are very high resolution simulations of the formation of Milky Way-like galaxies. So these are the original Auriga simulations that are now public for everyone to use. They have 10 to the 4 solar masses. There are some of them that have higher resolution. But now we are doing the second stage of this project, which is the Auriga superstars model. So you see now the same models, the same galaxies, but with these superstars. What is the advantage of superstar? That has a huge stellar mass resolution. Now our particles have the order of 10 to the 2 solar masses that we are able to resolve, and we have time snapshot of 5 mega years. So we can follow the orbits of the stars particles as a function of time with a great detail. So just you see the same galaxy, but now, for example, when you want to see the halos and the stellar stream, this is very beautiful. You see all this structure that is arising here that it was before there, but not so well resolved, right? All these shells and all these features. So this is for the halo, but the same for the disk, right? If you want to do these dynamics, you want to start see how the spiral arms, or in our case, lopsidedness, these simulations are very good for that. So this is the first example, something that Ariana did not long ago. We are working on this. What you see here is one of these superstars. This is the stellar disk, all the satellites, or these are only stellar particles. And I'm going to, hopefully you can see the movie. What you see on this is going to be time evolution of the surface brightness profile. And this is the A1 as a function of radius, and it's going to pass as the simulations evolve. And you see this structure, how it's moving, and then this massive satellite comes and start to generate this pattern that is sort of pulsating, you see, and evolving. So it's not something that is constant. It has some sort of amplitude and modulation that is, I will pass it again, it's going a little bit fast, but it's moving like a wave that is going up and down. So it's very complicated and rich behavior. With this simulation and with this now time resolution, we can explore it in detail and understand exactly how this is working and what is happening. I see, for sure, what you see here are sort of convolution between the lopsided and the spiral arms, which are generating these wiggles, but we want to correlate it and see what are the correlations between these two things. But this is all work in progress, and we will continue analyzing this in the near future. So now switching a little bit gears, I want to explore lopsidedness. How much time I have still?
10 minutes.
10 minutes, okay, good. Well, we try to go a bit faster, but I mean, I'm still looking at galaxy morphology, but now looking at the effect of the environment. So in lopsidedness, I didn't find anything significant, but we know that clusters are very good laboratories to study galaxy transformation, morphology, color, etc. So what we try to do is to explore how, yes, a difference between the properties of galaxies that are living in relaxed and disturbed clusters. And the way we selected disturbed and relaxed clusters is based on the shift between the center of mass of the gas distribution and the location of the BCG. So when the set is very large, we see that the clusters are relaxed and disturbed, and the opposite for the relaxed. So you here have two examples of a very disturbed halo. You see that it's interacting with another cluster that is in falling. So this is the BCG, this is the center of mass of the gas, is disturbed. But for a relaxed cluster, they are lying both in a very similar location. So what are the main differences that you can find in these two samples of galaxies? So what I'm showing here is a color magnitude diagram, basically for the relaxed cluster and for the disturbed. And in both cases, you see a very well-defined red sequence with some hints of a blue cloud. So what we did is to do these Hess diagrams to take the subtract one from the other and after normalizing them by the same number of objects. And what we find is that when we look at this difference, the red sequence is dominated, is more populated in relaxed cluster than in the stirred cluster, so it's much more significant. And the blue cloud, which is what I'm showing here, what is dominated. When it's red, it's dominated by the stirred clusters. When it's blue, by relaxed cluster. The blue cloud is dominated by the stirred cluster. The same happens for the star formation rate. We do this subtraction of the Hess diagram. We see that an excess of star forming galaxies in the stirred cluster and an excess of quench population for relaxed cluster, right? This can be seen here as well. I'm going to be a little bit faster because I have little time, but you see that, for example, in relaxed cluster, the red sequence is much more dominating, and in the stirred cluster we see, in comparison with the red sequence, a much more significant blue component. When we go outside the virial radius, same, we see that the stirred cluster have a very significant bluer population with respect to the main sequence, red sequence, than for relaxed cluster, right? If we explore the quench fractions in these two different cluster structures, we see that a low redshift, for example, 0.5, you see that basically in relaxed cluster, we have 90% of the galaxies that are within one virial radius are quenched already, and this fraction gets smaller as we get to the outer parts. If we look to the stirred cluster, the fraction of quench galaxies is significantly smaller, it's about 80%, and also it falls, but at a lower value. And a similar thing happened at higher redshift, right? When we compare these dashed lines as a higher redshift, what we do see at different times is that, for example, the difference between the fraction of quench galaxies in relaxed and the stirred cluster, the delta seems to be constant in both cases, whereas there is a dependency with galactocentric distance at higher redshift, right? So the fraction of quench galaxies are more similar between relaxed and the stirred cluster, closer to the central regions, but as we get to the outer region, the difference grows and grows faster at higher redshift. And so there is a strong radial dependence. So, in particular, what we wanted to see or to explore is whether our simulations are predicting a star formation burst and a post-quenching when two clusters are interacting, right? When they get close by, you have the both intracluster medium and start interacting, and some people are suggesting that this could actually enhance a burst of star formation rate, not in the VCG, but in the galaxies that are inhabiting this cluster, right? And this is what we wanted to see. So you have here two examples of interacting clusters, right? They were defined with the criteria I showed you before. And what I'm showing here is the change in the virial mass of the cluster as a function of time, right? We compute this change in the mass based on half of the dynamical time of the cluster. And we say that the measure, a significant measure happens when this delta m over m so with this time window, right? This period of the dynamical time is larger than 0.5. So when this happens, we say, okay, there is a significant interaction, for example, at this point. So what we do is to compare the present star formation rate with respect to the average star formation rate, also within the same time period of time. And what we find is that when we see a big merger, we see that the star formation rate grows, peaks, and then drops and sort of quench. The green line is showing all the galaxies in the clusters, excepting both VCGs, right? Because these are two interacting massive clusters, we remove the VCGs. And this is what these are all the other galaxies that are living in this structure. This is another example, the same structure. So when we do this stacking for all the interacting clusters that we have in our model, we see this clear signature that, again, as soon as there is a very massive merger, a very strong interaction, there is a star formation burst, but it's very short in time. And after the burst is super quenched very quickly, and all star formation activity sees going towards a more relaxed configuration. But we do find this in the simulation, this burst due to the interaction. I'm going to skip or move very quickly through this, but what we're trying to see here is where and when this quenching is happening. basically, very quickly speaking, what we find is that in cluster quenching tends to happen in low mass objects. As soon as satellites or galaxies enter into a group or low mass cluster, they rapidly quench. And then when they reach this more massive stellar cluster, they are already quenched, everything is quenched. So basically, pre-quenching tend to happen in low mass structure. Very quickly, let me skip this. But I wanted to show a little bit of all this machinery that we are developing, which is trying to generate detailed X-ray mocks from simulation. This is also work from Franklin Aldas. From the particles that we are getting from the simulation, we are generating a red frame spectrum for the X-ray emission, for the soft and the hard X-ray. We basically we use all the chemical evolution and the temperature of the gas particles, and we obtain these spectrums where we can actually measure from this basically mock the X-ray emission from this cluster, and these are maps of the of two clusters that are from the Millennium TNG simulation, that we can have very detailed X-ray emission in the soft X-ray band that can allow us to study and compare our results in basically comparing relaxed and disturbed cluster, now using something that is closer to observations and do other sort of very nice analysis. So we see also a very beautiful sort of structure that we want to explore, probably associated with RAM pressure stripping from galaxies that are interacting in this cluster. So now we have all this machinery, and what we're trying to do is to, for example, use proxy for cluster dynamical state, like the central shift, the concentration index, ratios between the kinetic and the thermal energy, and see how, for example, there are all scaling relations that can be defined for these parameters, and we want to see where there are departures between the scaling relations when we analyze relaxed and disturbed clusters, and for example, whether these departures depend on how, what is the stage of the interaction, right? Whether it's just happening as they get close by, how the departure from the classical scaling relations start to grow or decrease, and then how they come back again to lie down on the scaling relations that we have. I think I'm past my time. I have a few other things, but if I'm a bit late, I can skip this. And keep it here and take questions, not to make it too extensive. So thank you very much.
Do you have questions from the audience? No, I have none written here. Can you come close by?
So, hello, can you hear me?
Yes, now I can hear you. Hi.
Okay, maybe it's too close. Thank you for your talk. I have two questions. One about the mergers, another about the time scale of the perturbations.
Yes.
The first one, maybe I didn't understand it right, but did you consider micro and minor mergers when you were analyzing the simulations, if they have any relation with the perturbations?
So in general, what we explored both for this lopsided and for warps as well is that you need at least a 1 to 10 measure to generate perturbations that are global. Locally, yes, with smaller measures, you can see features that, for example, shift from the, if you look at warps, that the disk is locally above the midplane on average with respect to the rest of the disk. You can see perturbations associated with small satellites, but globally, that's something that you can see overall the disk. If they are smaller than 1 to 10, you don't get to see much effects in terms of this lopsidedness and warps.
Okay, and the second one is when you analyze the simulations also, how long the perturbed state lasts in the galaxies? Like once it's perturbed forever, or is there?
Yeah, Yeah, that's a good question, actually. This is something we really wanted to explore, and we were hoping to use the higher resolution simulation that I was showing here, because now we have very good time stepping to explore this. So, I mean, now that we have this model, what we find, like, if you see the two galaxies, let me show you something. Yeah, these examples. So in this case, you see that the galaxies are always lopsided if we, based on this threshold, basically at least during the last 6 gigayears of evolution, right? This is present day, and this has been the last 6 gigayears, and you see A1 is always above this dashed line, which means they have a significant amplitude on this mode. But we still see fluctuations, right? We see higher peaks and then decreases, and then again higher peaks. These peaks are associated with the satellite passages, but these strong modes, they are short-lived, at least in these models. They do not last very long. The overall amplitude, the overall fact that they are lopsided, it has lasted over the whole period that we study. So you could say, okay, this is a very long-lived perturbation, but the peaks associated with satellites and with significant interaction, that seems to be short-lived. So that's basically what we are finding so far.
Thank you. Thank you very much.
You're welcome.
More questions? Not, I have some, but let's leave space for people to speak a bit. Write down your questions in the Google Doc. Do we have questions online or in YouTube? So I have a couple of questions. One is, in the analysis you're doing with the multi-band surveys and thinking about LSST and so on, do you see any enhanced lopsidedness or enhanced A parameter in different bands or in when you're looking at?
Yes.
So,
Yes, I mean, yes. So in principle, we try. The idea at the end of the day is try to go to the band that most closely would actually represent the stellar density, right? You want to see the mass distribution rather than the light, because if you look at, for example, bluer bands, this A1 will be dominated by these very bright stars or the spiral arms, and that's what is going to dominate all the features that we observe. But in general, we see that when we look at the populations, that if we change the band, there are shifts in the amplitude of this A1, but it shifts for both, for the symmetric and for the lopsided in similar ways. It's like you just change the 0 point. So so far, what we find is that it's not a big issue in terms of differentiating the two populations. Nonetheless, we would like to go to the red or infrared bands in order to get closer to the density distribution rather than the light itself. Yeah, I think I have a plot somewhere here. Let me see if my backup slides is. I used to have one, but no, I removed it. But, yes, maybe here. So look, this is for example, the mass distribution. What you could get if you look in the C band and what you could get in the R band, right? I mean, these are just two examples. So you see sort of the same behavior with a little bit of shift, right? And so it can be done with all of these things, but you need to know that there are biases toward higher amplitudes if you go to the light and depending on the band.
yeah. Regarding the definition of lopsidedness, could you say that it's like an umbrella term for and would incorporate ramp pressure stripped galaxies?
Yeah, I mean, like, for example, if you want, there is a very nice review from Chanda Yog where she discusses lopsidedness. And indeed, I mean, like, for example, I think this is taken from her review with Combs that she wrote it. So you see now M81 is very beautiful lopsided, and when she's talking about lopsided, you see this, that is a classical jellyfish ramp pressure strip galaxy, right? This is also considered a lopsided galaxy. Just the term or the reason why these are lopsided are different, but indeed, this is another category of lopsided galaxy that would be interesting to study because, well, I mean, like, this directly goes to ramp pressure stripping, right? I mean, and the ICM.
We did some work some time ago with a merging cluster or 4 merging clusters, and we found the increase in jellyfish galaxies in the borders of these merging clusters, and maybe it seems to be related to what you're finding.
Nice.
Well, I can see the reference.
Yeah, please.
Nice to see that. And last but not least, no more questions? No from the students? Not this time? Okay. What is the resolution of the latest Auriga simulations, and can you form star clusters?
No, so star clusters are not yet there. I mean, I think that the new Auriga simulations are very, very powerful and very nice in terms of tracers of the dynamics. But nothing in the physics of the Auriga simulation has been changed. So whatever was believable before is still believable now, but no new physics are implemented. The only thing that we do is that when a star particle is born from a gas cell, rather than forming a unique star particle, we form 64 star particles. We provide these 64 star particles like a velocity dispersion so they don't become bound, which is consistent with the velocity dispersion of the turbulent area where they are born from the gas. So they are sheltered in a reasonable real way. And we test that this lower mass resolution does not have an important effect with the dynamical heating due to, softening and this kind of thing. That has been very well tested, and we are about to submit a paper with all this method described. So it's just more tracers of the underlying potential, not more physics. So it's good for dynamical analysis, as I say, like you want to study how, for example, the spiral arms are perturbing the flows in the disk, right? I mean, you have torques and this is very nice because you have now very good resolved structures. But yet we don't have anything new with regards to the equation of state or how we measure the IgM, intergalactic medium, or how star formation happens. Is the same prescription. So clusters is not something that we would trust. I mean, it would be something more non-trustable than realistic.
Okay, thanks a lot, Facundo. Let's thank you.
Thank you, everyone.
Thank you very much. Now we
Cool.
can go for in the next room.
Okay.
So I'll send you the YouTube link later on.
Thank you very much,
Unless
Anna.
You